Okay, in this video, I'd like to talk a little bit more about how to solve different types of trigonometric equations. Sometimes we see trigonometric equations written in what we would say is a quadratic or polynomial form. And the giveaway here is that we start to see exponents along with our trig functions. Now, you may more easily recognize this if this had been written as not 2 times sine squared, but 2 times x squared minus 3 times x plus 1 equals 0. So essentially what I've done is I've let the letter x be the same as sine of theta right now. Now again, our goal is to find the answer in terms of theta. So after I solve this problem in terms of x, I'm going to come back and make this substitution to make sure that I solve for theta. So if 2x squared minus 3x plus 1 is equal to 0, we've got a variety of methods that we can use to solve that. A quadratic formula, completing the square, etc., etc. I would probably use the factoring method if this function is factorable, or if this expression is factorable. And in this case it is, because 2x times x is x squared, 1 times 1 is 1, and if I'm thinking of the foiling method, all I would need is a negative sign here and here, and then this group would FOIL back together to make the original expression. So we've got this factored, and when I've got a pair of factors that multiply together to equal 0, then either 2x minus 1 is equal to 0, or x minus 1 is equal to 0. Either of those factors could be equal to 0. And so this tells me that x is equal to 1/2, or x is equal to 1. Now that would be fine if we were looking for an answer in terms of x, but we're not. We're actually being asked to find our solution for theta. So now I'm going to make that substitution. X is being turned back into sine theta. So now the question becomes, when does sine theta equal 1/2? Or when does sine theta equal 1? And both of those solutions can be found with the unit circle. No calculators are needed. Sine of theta would equal 1 up here at the top of our graph, so that's the position pi over 2. And sine of theta equals 1/2 at these positions, right? Our y value has to be 1/2. And so this would be theta, I should have noted this here, theta is equal to pi over 6, and theta is also equal to 5 pi over 6. So all three of these solutions are solutions to the original problem, and they exist within a unit circle as described by our domain restriction. As a matter of semantics, if I were writing this solution on paper, I would make sure to take the time to list these in ascending order. This is just something that we often do when we have a set of solutions. So pi over 6 is the smallest, then pi over 2, and then 5 pi over 6. However, in Math Excel, I don't believe the site is going to be that picky. I'm certain you'll have to separate your answers by commas, but I don't think you'll need to list them in ascending order. So here's another example. Again, I see this sine squared, so I might be thinking, well, let's use the quadratic approach, but then if I look on the other side, I've got a cosine, and these two are not the same trig functions, so maybe the quadratic approach isn't going to work. So changing sine squared to x squared might not be the wise thing to do. Because if I change sine of theta to x, then I might have to change cosine of theta to y or some other letter. And to have two different variables just isn't all that helpful. So what I would like to do is follow the instructions, their little hint here, and use some sort of identity to see if we can get our trigonometric functions to match. Is there some way that I can rewrite cosine in terms of sine, or is there some way that I can rewrite sine squared in terms of cosine or cosine squared? And I'm actually going to use this one over here. I'm going to change sine squared because I had mentioned this in weeks past, that when we see the sine squared or cosine squared, that might be an indicator that we could use a Pythagorean identity. So let's take a look at this. If we go back to our identities list, remember sine squared plus cosine squared is equal to 1. So what that means is that sine squared by itself would be 1 minus cosine squared. And if I make this substitution, if I change sine squared to 1 minus cosine squared, well, at least we've now got the same trigonometric function all over the place. So let's see what happens if we make that substitution. Now, what's interesting about these trigonometric equations is that sometimes these substitutions could be mathematically correct, but they may not lead us to a method to solve a problem. So making this substitution here is 100% mathematically permissible, but the luck of the draw might be that it doesn't get us anywhere to a solution. And to be perfectly honest, we won't know that until we do a little bit of work. This is part of what gives some students frustration in these problems, is that sometimes you're doing everything correct, but you end up without finding the correct answer, or any answer for that matter. And I can understand being frustrated with that, but again, that's just the way things go in higher level mathematics. Sometimes we've got to pick and choose our battles and be steadfast in looking for solutions. So while I was chatting there, I just did a little bit of math. I distributed my 2, and then I moved these 2 terms to the left-hand side because it is starting to look more and more like a quadratic equation now. And so now I've got 2 cosine squared plus 3 cosine plus 1. And again, if I make a variable substitution for just a second, if I say that x is the same as cosine theta, then I can imagine this problem as 2x squared plus 3x plus 1, and it looks awfully familiar to that last equation that we just solved. So factoring, I hope, works here. So 2x times x gives me x squared. 1 times 1 gives me 1. And if I think of the foiling process, the outside and inside products have to sum together to equal 3x. And that's going to happen if I use 2 plus signs here. So we've got factors that multiply to equal 0. So therefore, 2x plus 1 is equal to 0. And x plus 1 is equal to 0. And I can solve this relatively easily. X is equal to negative 1/2. X is equal to negative 1. But now I want to make sure that I make the substitution back. I said that x was equal to cosine. So when does cosine theta equal negative 1/2? And when does cosine theta equal negative 1? Here again, considering my unit circle, cosine of theta equals negative 1 here. Cosine theta equals 1/2 here. And whoops, sorry, this is supposed to be negative 1/2. So negative 1/2 here and here. So if I'm going to report my final answer, I would say something like this, that theta is equal to, well, the smallest angle is this guy, which is 2 pi over 3. And then the next largest would be this guy here, pi units. And then finally this guy down here, which is 4 pi over 3. And we've got our solutions to that example. And again, all of these solutions exist within a single unit circle as described by our domain restriction at the top. So in this last example, you might try doing the same thing as before. You'll notice that cosine squared and sine are included in this equation, and it would be nice to have the same trig function if possible. So I'm going to use that same Pythagorean identity, and I'm going to rewrite cosine squared as 1 minus sine squared plus sine theta equals 2. And if I were to solve this, I could clear the parentheses. In fact, I don't even need them here. I don't particularly like leading a quadratic with a negative sign, so I'm going to move all of these to the right-hand side. This is just a personal bias of mine. You could do what you'd like. So I'm going to say that 0 is equal to positive sine squared minus sine theta. And then this, I'm subtracting 1 over, so this will be a plus 1 on the right-hand side. So in my mind, I'm going to think, well, is this factorable? I could say that x is the same as sine, just to help me see this a little bit more clearly. X squared minus x plus 1. Um, hmm. Well, clearly x times x equals x squared, and 1 times 1 equals 1. But if I FOIL this back together, the outside product 1x, the inside product 1x, those two can't add or subtract to make this middle term here. So this is not factorable. Not factorable. So now we've got to think, well, what are the other options to solving a quadratic? Can we do this by completing the square or any other method? Well, certainly. But if we're going to go the completing the square route, I might as well just take it one step further and consider the quadratic formula. Our a value is 1, our b value is -1, and our c value is also 1. So I can very quickly calculate my discriminant, which is b squared minus 4ac. And if you've not seen this before, this is how I teach quadratic formula in my Algebra 2 class. We always list our A, B, C values first and then calculate the discriminant immediately afterwards, so that our solution can be found by using this format of the quadratic formula. Rather than memorizing the entire thing in one large chunk, we can say that x is equal to the opposite of b plus or minus the square root of d, our discriminant, divided by 2a. And I also like to emphasize this too, that if we consider what type of answer we get for this discriminant, then we can predict what type of solutions we'll see at the very end. And this discriminant ended up calculating out to be a -3. Now think of what's going to happen if I substitute -3 in place of this d value. Well, I'm being asked to take the square root of a negative number, and the square root of a negative number is a non-real result. So fortunately for you, I'm not going to ask you to find solutions to trigonometric functions that contain imaginary numbers, so we'll go ahead and stop here. This was not factorable, and the discriminant is less than 0. It's negative, so therefore, these little triangle dots means the words therefore. We have no real solution, and we can actually stop there. If you see this question in Math Excel, I think this becomes a multiple choice option. Option A is to list the solutions. Option B is to indicate that there are no real solutions, and that's what I would choose for this example. The video is getting quite lengthy here, so, well, what the heck. It's already 13 minutes long. I'll go ahead and finish this one out. And then I'll let you work on the optional homework and reach out to me if you've got any additional questions. This type of problem is pretty interesting because while we can utilize some algebra techniques to solve it, ultimately the solution comes from your understanding and observance of the unit circle. Now, we do have sine evaluated at -theta, and what I want to draw your attention to is our old trig identities. We have these even-odd identities that hopefully you memorized. When I see sine of -theta, I'm immediately going to change that to a negative sine of positive theta. That's part of our even-odd identity group. So if I'm solving this, I'm going to say that cosine theta is going to subtract a negative sine of positive theta. I'm just making that substitution because of the identities. And then I'm going to clear these parentheses. And now I've got cosine theta equals sine theta. And again, it would be nice if these two were the same trig identity, but in this case, there's no real easy way to change a cosine into a form of sine. Now, if one of these was a cosine squared or a sine squared, that would be different, but this is regular old cosine and regular old sine. So let me share with you a little bit of a trick. Theta is the same angle, right? Theta, this letter is the same in every component within this equation. So we're kind of asking ourselves, when does the x position from the unit circle, this cosine component, add with the y component of the position in the unit circle to equal 0? Or in other words, if I subtract sine theta to the other side, when does cosine theta equal the opposite of sine theta? When does the x coordinate equal the opposite of the y coordinate? And so we got to switch out of our algebra brain for just a second and think geometrically here. There are 4 positions around this unit circle where the x and the y coordinate are numerically the same, except for maybe their signs. So this position has an x value of root 2 over 2 and a y position of root 2 over 2. But if I add x plus y, I don't get 0 in that case, right? If I add x plus y, I don't get 0. Or x, in other words, is not the opposite of y. So this solution's no good. But if I swing to this position here, now I have an x value of root 2 over 2 and a y value of root 2 over 2, but negative. Now x plus y does equal 0. So that's a solution inside our unit circle. This one down here is no good because root 2 over 2 is negative and root 2 over 2 is also negative here. The sum of those two does not equal 0, so I don't like that. But in this position, it does add to 0 as well. Oops, you know what? I had my signs messed up back here. Let me fix that. It doesn't change our answer, but my x value was negative and my y value was positive. Over here, my x value is positive, root 2 over 2, and my y value is negative. Again, the sum of these two does equal 0. So mentally, geometrically, we're perceiving this algebra expression as positions inside our unit circle. And again, that's kind of a helpful trick that we can utilize when solving these trig functions. We've got to be able to switch back and forth between the geometric and the algebraic representation. And I would argue that theta in this case is this angle measure, which is 3 pi over 4. And then theta is also this angle measure, which is 7 pi over 4. And that would represent all of our solutions inside of a single rotation of the unit circle. So hopefully that helps, and thank you for sticking along with me if you have for the entire length of this video. Certainly reach out to me if you have questions or if you'd like to talk about specific examples that you're encountering in Math Excel or on the optional homework. Thanks for watching.